In the previous videos, we focused on Taylor polynomials as approximations for the functions that are sufficiently differentiable. Now, what if a function is infinitely differentiable? So suppose that f is a function on an open interval, a is a member of this open interval, and suppose this function is infinitely differentiable at a, right? So this means that fa exists, f prime a exists, f double prime a exists, and so forth, right? So all the kth order derivatives in a exist for any k being a natural number. Okay, then we can build up, we can at least try to define the infinite Taylor polynomial or the Taylor series. So what does it mean? Well, we define the following series. The Taylor series of f at a is the following power series. Is the power series which is defined as an infinite Taylor polynomial, right? So we take fa plus f prime x minus a plus f double prime a divided by 2 factorial times x minus a squared, etc., etc., right? So basically, the Taylor series is defined as the infinite sum where the nth term in this series is just the nth derivative of f in a divided by n factorial times x minus a to the power n. So this is the basic assumption, right? So we have this function defined on an open interval, a inside this open interval, and we know that the kth order derivative in a exists for all k, right? Okay, so now recall that we can define the remainder, right? So the remainder of the nth order Taylor polynomial, it's just the difference of the function and the values of the Taylor polynomial. Now suppose that for n to infinity, Rnx for a given x is just equal to 0. Yeah, this means that the limit for n to infinity of fx minus Tn of x is 0. Right? So this means that fx equals the limit for n to infinity of nx, right? So in that case, if we can show that the remainder terms for n to infinity go to 0, then we would know that fx equals its Taylor series, right? Well, as an example, just recall this function, the exponential function. Let's look at Taylor approximations in 0, a equals 0. And we've already seen that the limit for n to infinity of the remainder terms is just equal to 0. And we use Taylor's theorem for that to show it, right? So as a conclusion, we find that fx equals the limit for n to infinity of the Taylor polynomial. So fx equals the infinite Taylor series. So we get a different description for the e to the power x in terms of a power series, right? So, and this identity holds for all x in R, right? Okay, we might check for convergence, right? So we have a look at this power series here on the right. This thing converges for all x since we can just apply the ratio test, right? So just apply the ratio test where an equals x to the power n divided by n factorial. And then we get xn plus 1 divided n plus 1 divided by x to the power n divided by n factorial, which equals x to the x divided by n plus 1, and this one goes to 0 for n going to infinity. Yeah, so we see that the the radius of convergence for this power series is infinite, and fx is always equal to its Taylor series.